All right, so we're going to introduce the concept of ice tables with this first problem that we see both as the last slide in the equilibrium slides that we covered last Thursday, before the third midterm. And this is problem number 5 on the chapter 13 worksheet. And so there's this reaction given to us here, which is S8 gas goes to 4S2 gas. And if you want to follow along in the worksheet, I totally suggest you get that out. This is on page 3, first problem at the top there, number 5. And we're told that this reaction is happening at 25 degrees Celsius. And we're also told that initially we have 1 atmosphere of S8 gas, and that's being placed into a sealed container, and then it's being heated until we get to a partial pressure for the S8 of 0.25 atmospheres. And then what is Kp is what it's asking. So our goal here, write this down. Our goal is to figure out what's Kp. Now, a little bit about the way this problem is worded. On exams, I tend to be a little bit clearer about this, or, you'll get used to kind of seeing this wording. But this whole thing that it's saying that we're starting with initially 1 atmosphere of S8 and placing it into a sealed container and heating it until the partial pressure of this equals 0.25 atmospheres. We're assuming that this reaction is basically going to come to sort of a stop. But remember, we know that with equilibrium reactions with this double arrow, that it's not truly stopping, right? It's still going forward and backward and forward and backward. But the values for the partial pressure or for the concentration, if you were monitoring that, would be coming to some constant value and it would be staying there. And so the way this problem is worded, we're supposed to reasonably assume that if we're heating this substance at 1 atmosphere until it gets down to 0.25 atmospheres, that's the point where we're reaching equilibrium. And so that's telling us that the partial pressure at equilibrium for the S8 is going to be 0.25 atmospheres. So we're starting at 1 and we're coming down to 0.25. And so those are the only 2 values that you're being given here, and we need to know what to do with those values. And this is where this technique that's referred to as ice tables or rice tables is going to come into play. Rice comes from the fact that you would start off by calling your reaction the first row in this this procedure, and then ICE is what comes after the reaction. So notice here, I tend to prefer to use the term ice because these are the rows that we're actually going to be filling out. And often when you're given a reaction on a problem, like on a worksheet or something, if there's nothing below the reaction, a lot of times I'll just put ice right below it and I'll start filling out this table. But the term rice comes from the fact that the table always starts with the reaction. So you could put an R at the top here to help you remind yourself of that if you find that necessary. For me, I know that I'm going to be filling out these I, C, and E rows with some values, and so I just like to mark those. Now, what do I, C, and E stands for? Well, I is going to be the initial amount, C is going to be the change, and E is going to be the equilibrium. So notice here, that's what ICE stands for, is initial, change, and equilibrium. The initial values are going to be exactly what you're usually given in the problem. So we're told in this problem we initially have 1 atmosphere of S8 gas. So I'm going to put 1 atmosphere down for the S8 gas. Now, we're not told anything about the S2, and when that's the case and when it's worded in the way that it is in this problem, it says initially 1 atmosphere is placed into a sealed container. That implies that we don't have any product at that point, right? We're just starting off by putting our reactants into a container, and that's a very common starting point for a lot of reactions that you would do in the lab. You would start with reactants. But we know that with this reaction having this equilibrium, that if we start with reactants, we are going to form some product, but we're not going to go completely to products, right? We're going to end up at some state where we have a little bit of this reactant still present, and that's what's indicated in this problem by saying that we're going to heat it until the equilibrium value for this S8 is 0.25 atmospheres. So notice that I've got my initial value, I've got my change, which we'll talk about in a second, and then I've got my equilibrium values. Well, in this problem, I'm told that my equilibrium value for the S8 is going to be 0.2. 5 atmospheres. So I can go ahead and fill that in already as well. And then going back to what I was saying, if you're starting with just this reactant, we can reasonably assume that you don't have any of your product at this point. Okay, so we filled out a couple things in this ice table so far. Let's talk about how we proceed to filling out the change row and finishing off this equilibrium row. So for the change row, we need to consider which direction this reaction is going to proceed in or is going to shift in order to reach equilibrium, because we're not at equilibrium at the beginning here if all we have is reactants. And the best way to think about this is to remember your Q versus K sort of situation. Q in this situation, if I set up my Q expression, remember it's going to have the same expression as K. So I'm going to have my products, so S2 over my reactants, so S8. Now I'm dealing with pressures in this problem, and I'm looking to solve for a Kp, so I'm thinking about Qp in this case, and that means this is the pressure of the S2 and the pressure of the S8 in this expression, products over reactants. And then those of you that are following really closely here are going to notice I forgot my 4 out in front here of the S2. That's going to be to the 4th power here. So if I note here, what's happening when I have 0 and 1? Well, I have 0 to the 4th on the top, and I have 1 atmosphere on the bottom. And 0 divided by a number is basically going to give you a 0. And so notice here that this is a situation where Q is equal to 0. And if Q is equal to 0, that is always going to be less than our value of K. Because remember that K can take a large range of values, right? It can be really, really small or it can be really, really large, but it's always going to be greater than 0. So in these situations where you start with only reactant and no products, Q is always going to end up giving you a 0, which is always going to be less than K. And when Q is less than K, we need to shift towards products to get to equilibrium. So again, some of this is common sense, but sometimes, you may start with values of both of the sides of the equation. And so if this was not a 0 value and it was some number, this is always what you want to do first to determine which way you're actually shifting, because the direction you're shifting in to get to equilibrium is going to dictate what this change row is going to look like. Again, a lot of these problems will start with all reactant and no product. And so most of the time it's reasonable to just use common sense and be like, well, if I start with all reactant, I have to shift towards products, because the nature of equilibrium is that I have some amount of reactant and some amount of product present. And so if there's no product present at the beginning, I have to move that direction. But when in doubt, you can always sit down and think about, well, what is Q going to equal in this situation, and how's that going to compare to K? Now, in some problems, we're going to see a little bit later, you'll be given a K value for a problem like this, and you'll be solving for something different, right? In this case, we're actually trying to solve for K, so they didn't tell us what it is. So if we did have some value here for the S2, it would be really hard to compare Q and K because we wouldn't know what K is, so how would you compare them? But because we have a 0 here and we're getting Q is equal to 0, we don't even need to know what K is. We know that K is going to be greater than 0. And so this kind of gives you the reasoning for how to apply logic in this situation to feel better about assuming that this is going to shift towards products. So I hope that is clear to everyone, but do feel free to ask questions if you're confused about how that works. All right, so let's go back to this change row. And recognize now that if we're going to shift towards products, that means some amount of this S8 is going to react. And so we're going to lose some of this 1 atmospheres. And we can kind of see that happening with the fact that we're going to end up at a smaller value at equilibrium. So we're obviously losing S8 as this pressure is dropping. We know the pressure is related to the amount of particles present. And so we're losing that amount of S8. Over here, we know as we shift towards products, we're going to gain some amount of S2. So we know that by the end here, we should have some pressure of S2 present. So how do we represent this in the change row? Because, in a lot of these problems, you're not going to know exactly how much it's changing by. So we're basically going to use a variable here to show how the change for the reactants is related to the change for the products. And since we're losing some amount of stuff here, we're going to call this value a negative on this side because we know that we're going to lose reactants. And we're going to just use the value X as a placeholder here for what that change represents, because we may not know yet until we think through this a little bit further what x is actually going to be equal to. Also notice that over on this side, we're gaining, so we're going to have a positive value, and we are also going to still use x because there's always a relationship between these amounts, right? If 1 mole of this reacts, we're going to end up with 4 moles of our S2. And so this change that we're seeing, this change of x, has to be related to the positive change in x over on this side by that same stoichiometric ratio, that 1-to-4 ratio. So basically what this comes down to is you want to use your coefficients out in front of the reaction to represent the coefficients out in front of x. So you notice I left a space here because over on this side, since we have that 4 out in front of the S2, we need to also include the 4 over here. And all this is really showing is that for every 1 mole of S8 that we react, we're going to get 4 moles of S2. And if 1 mole has a specific pressure associated with it, then every amount of pressure that we lose, 1 unit of pressure that we lose, we're going to get 4 units of pressure being added over on this side. Okay, so that is what that is representing there. For the last row, what we usually do is we add together the top 2 rows. And so you would know that equilibrium here is going to be equal to 1 minus x, and then equilibrium over here is going to be equal to 0 plus 4x. So on my equilibrium side over here, I know, because I don't know anything about S2 yet here, and I haven't figured out what x is yet, I know that this is going to be equal to 4 times x for my equilibrium value. Now, we already filled in the equilibrium value for the S8 because it was given to us. But notice that this now gives us a relationship that allows us to solve for x. Because if we're saying that the sum of these 2 rows has to equal this last value, and we know what that value is, then we can actually set that up now as an expression. So 1 atmosphere minus x has to be equal to 0.25 atmospheres. And so now if I solve for x in this situation, I'm going to get that x is equal to 0.75 atmospheres. All right, well, if I know what x is, now I know how to solve for my S2 partial pressure, right? So I can take the partial pressure of S2 at equilibrium is going to be equal to 4 times x. And if I know that x is 0.75, 4 times 0.75 is going to be equal to 3 atmospheres. All right, so notice here that we were able to solve for the partial pressure at equilibrium for the S2 as being 3 atmospheres, and we already know that the partial pressure at equilibrium for S8 is 0.25 atmospheres. Once you know the values at equilibrium, you can solve for K. So now we're going to come back to our Kp expression, and we're going to, again, think about how this is set up. So it should be the partial pressure of our products, partial pressure of S2, to the 4th power because of that 4, over the partial pressure of the S8. And so if I take my pressure of my S2, which was 3 atmospheres, and I take it to the 4th power, and then I take my partial pressure of the S8, which was told was going to be 0.25 atmospheres, then I can combine this all together. So 3 to the 4th divided by 0.25 is going to give me a value of 324 for Kp. And that essentially is the answer for this problem. So thinking a little bit about what that answer implies, notice that at equilibrium, we're expecting to have a little bit more of the S2 than we do the S8, but that they should be somewhat comparable. And if you're looking at what those actual partial pressures are, you can justify this value by recognizing that, well, my partial pressure at equilibrium for my S2 is 3 atmospheres, and my partial pressure for my S8 is 0.25 atmospheres. So I do have more of the S2, but they're fairly similar to each other, right? They're only 1 order of magnitude off in their values. So that does kind of justify a slight weighting towards products with them being somewhat comparable values, which is what this value is in range of. And if you're having a hard time seeing that, remember that 324 is going to be 3.24 times 10 to the second. And so remember, our intermediate values fall between 10 to the 4th and 10 to the negative 4th. And so this is definitely an intermediate value with a slight weighting towards the products in this situation. Okay, so this one's pretty straightforward. I use this again as a way to introduce what this ice table process kind of looks like, but I will point out that this is one type of approach for ice tables, and let me point out the features that make it one of the types. That is that in this problem, you don't know what K is. And so you're solving for K by figuring out X by some bit of information that they're being given to you in the problem. It was crucial in this problem that they told us something about the equilibrium, because without knowing something about the equilibrium values, there's no way to solve for X. Unless you have K already. And since we don't have K, we need to still have some way to solve for X. And in any one of these ice table problems, your first goal is always going to be to solve for X. But the way that you solve for X can vary depending upon the approach for the problem. This type, that approach involves utilizing information in the problem that you're given about equilibrium to figure out what X is so that you can get your equilibrium values, plug them into your K expression, and solve for what KP is actually going to be. And so that's one type of approach. Now I want to point out to you guys that the next problem on the worksheet it's problem number 6. And let me just point out here that it deals with PCl5 gas goes to PCl3 gas plus Cl2 gas. Okay, so that's the reaction that we're dealing with. And I want you guys to kind of try this one on your own. The key has been posted for this worksheet, so you can look at the key if you need to, but try it out first with what we just talked about on the number 5 problem. And I'm going to give you a little tip here, because this one's very similar in that you're asked to solve for K. So you're going to need to solve for X in your ice table by figuring it out using some information about the equilibrium. And the only information they give you about equilibrium in this problem is they tell you that the total pressure is equal to 0.830 atmospheres at equilibrium. Now, let's note here that if you're given a total pressure, this doesn't help you immediately figure out the partial pressures of each one of these things at equilibrium. It's a little bit more complicated because this is the sum of all of those partial pressures at equilibrium. Whoops, sorry. I didn't mean to write a plus sign there. Just get rid of that. Let me write this out, that the total, let's think about what this represents, right? The total pressure is the sum of all the partial pressures. So we would have the partial pressure of the PCl5 plus the partial pressure of the PCl3 plus the partial pressure of the Cl2. So, and these would all be the values at equilibrium, right? So if you figure out your ice table for this reaction, you're going to be able to get to the point where you're going to have an expression at equilibrium for every one of the things in the reaction that's in terms of X. Because in this problem, we don't have a value for one of the gases that we can put in the equilibrium row. So you're going to have to work through the initial values, the change, and then come up with your equilibrium expressions in terms of X for each one of the gases. And then once you get those expressions in terms of X, you can plug them into these partial pressure points and set it all equal to 0.830 atmospheres and then solve for X. So this one's a little different in that you have to use a total pressure at equilibrium to figure out, using the ice tables, what X is in each one of these individual partial pressure terms. So I challenge you guys to take a look at this problem on your own first. I'm not going to do a video on this one. There is the key that you can look at, but do feel free to come to me with questions if you're confused about this. It's very similar to the one that we just did, with the exception of there's just a slightly different approach here for how you're going to solve for X. Okay. The one last thing I want to mention here is what happens when you've got a reaction that has something in it that is not normally included in the equilibrium expression. So I'm going to go back to problem number 2 just to grab the reaction out. So this was the reaction we looked at in problem number 2 on the worksheet. Looks like this. And I want to point out here, if we write our ice table out for this problem, okay, so ICE, and let's pretend this is a situation where we've got, let's say 1 atmosphere of H2S gas at the beginning. Let's say we've got 1.5 atmospheres of O2 gas at the beginning, and then we don't have any water present. Whoops, sorry, not a line. Let's say 0 atmospheres present for the water. And then you've got this solid in here, right? If you're told information about the solid in an ice table type problem, note that this does not get incorporated into your K expression. So that also means we're not going to worry about it in the ice table. And what I usually do is just put a line through all 3 of the rows whenever I see a solid or pure liquid present, and I just put that line in there, and that reminds me that I don't need to consider this species at all. Now, if we were going forward with the ice table here, notice again we have 0 for our product over here, and it also wouldn't matter if we had some amount of sulfur. As long as you have anything on the product side that's a 0, that means that you're going to shift towards product, again, because of that whole relationship about Q being 0 essentially and always being less than K. But if you're going to set up your ice table here for the changes, note here that we have a 2 out in front, so this would be minus 2x. We have a 1 out in front here, so this would just be minus x. We're not worried about the solid. And then over on this side, we'd have plus 2x. So then at equilibrium, you would have 1 minus 2x. You'd have 1.5 minus x. And then you'd have 2x. One of the things I like to do when I write out my equilibrium rows, these can get kind of messy sometimes and can kind of get pretty long and crowded. And so I often will just put parentheses around the terms just to point out to myself and make it really, really clear what the term is for that chemical. So I encourage you to do that as well, because it really does kind of help you keep things separated nicely. I want to point out here again that you got to pay attention to your coefficients, right? So since we have those coefficients out in front for 2 of these species, that's why we have a 2 here. You want to pay attention to it should be negatives on the reactant side and positives on the product side if you've identified that you're going to shift towards products, and that's usually going to be the case. And then that the equilibrium row is always going to be adding together these top 2 rows. So I plus C is always what you're going to get for equilibrium. Now, just to kind of finish this out conceptually, I'm not going to solve anything here. But if I was going to plug in for my KP expression here, I would have the partial pressure of the water squared all over the partial pressure of the H2S squared times the partial pressure of the O2. Right? And so if I was going to plug in all these values into this expression, I would have 2x squared on the top. I'd have 1 minus 2x squared on the bottom. And then I'd have 1.5 minus x. So notice what I'm doing there. I'm taking the terms that are in terms of x, and I'm plugging them into the appropriate spots in the expression. Now there's something we're going to do next to deal with a situation like this. It'll be in the next video. I'll do an example of one where we're going to actually solve an expression like this and solve for x in a slightly different way than what I showed you in this video for problem number 5. But if you want to go ahead and attempt number 6, now I think you've got enough basics down to know how to set up these ice tables. Just to recap again, the whole reason I went through this process was just to point out what you do when you have a solid or a liquid and it doesn't get included. You just ignore it in the ice table. I don't believe any of the problems in the worksheet actually have one of those situations, but you might run into them on the homework, or you might run into them if you're doing problems in the textbook. So do feel free to send me any questions you have if anything in this video was unclear. But otherwise, I'd suggest you go attempt problem number 6 and then move on to the next video.